Oh, what's up, guys? So today we're gonna do properties of limits and simplifying. I've basically already done this video, but it was too long, so I had to delete the video. A lot of these properties are already solved, so we'll go through them much quicker. But let's go. So we're doing properties of limits and simplifying. I just decided to add simplifying. I think it's pretty useful. So first, let's go addition. Let me go ahead and delete this. Well, I don't have to delete it. That's pretty important. I don't want to delete that. So basically, when you're this is just an expression for addition on the left side. Limits as x approaches c of f of x plus g of x. So whenever you have like an expression like this, you have two functions that are being added, and you're approaching c, which is just a variable. This is basically just this is the same thing as the limit as x approaches c of f of x. It's the same thing as the limit of x approaches c of f of x plus the limit as x approaches c of g of x. So when you're doing an addition, this is what you have to turn it into. So you have to find each individual limit of you have to find the individual limit of each function first. So this only works if the limits actually exist. So let's just say in this first situation they do exist. Ignore the top one for now. Let's just say it exists. Let's just say that's the limit of f of x is 2 and the limit of this is 3. Let's just say that they exist and those are the limits. You just add them since they both exist. Now this becomes a little bit more complicated when you have to when one of them or both of them don't exist. So if they one of them don't exist, let's go ahead and retract that. You have to go through it another way. So instead of adding just the limit of f of x plus the limit of g of x, now you have to add each individual side. So what I mean by that is here I started with positive, I'm pretty sure. Um, just write that. So you can start with either side you want, but here I started with the right side, the positive side. So first you just find the limit of as x approaches c from the right of f of x plus the limit as x approaches c from the right once again of g of x. So you just add the limit of each side for each function. So limits of f of x from the right plus the limits of g of x from the right. So uh, let's just say that these most of the time do exist. So let's just say that's 1, and let's just say this is 2. So this sum is going to be 4, and you do the 4. You do the exact same thing for subtraction. So I'm not going to write that, but let's just pretend that these positives, this positive right here, that's just the negative. Uh, uh, yeah, so let's just pretend that instead of a positive, this is just asking for the left side. So the limit as x approaches c from the left of f of x plus the limit as x approaches c from the left of g of x. So you add the limit of f of x from the left plus the limit of g of x from the left. And now let's say maybe this once again evaluates to, oh, sorry, I was going to write 4, but it should have been 3 plus 1 if they do exist, and that's 4. So if the two sums of the individual sides of each function equate or they're the same, that's going to be your answer to the limit. If they're different, for example, maybe if this was 5, not 3, I'm sorry, maybe if this was 5, not 3, and this was 6, um, that would not equate, and so that would not have limits. They have to have the same exact sum. So let's move on to subtraction. And basically, as long as you just take this into account, the individual side like process, you can basically do any property. It's the same thing for every single property. Subtraction, same exact thing. So the limit, let me write it just down. X of c of f of x minus exact same thing. Just write it quickly. Xc of g of x. Oh, alright, just pretend that's g of x. So you just find the limit of f of x and then minus the limit of g of x. Once again, if they do exist, let's just say that's 4 minus 2. The answer becomes 2. That's the limit, as long as the limits exist in the initial phase. If they don't, once again, you have to resort to the individual sides. So it's just for the sake of time, so that I can upload this. I'm not gonna write down each individual thing, but same exact thing is up here. You can start with whatever side you want to do, but you have to go with the same sides. So let's just say the limits as x approaches c from the left of f of x for subtraction, using the addition for like a model up here. So the limit is of as x approaches c from the left of f of x minus the limit of x as x approaches c from the left of g of x. So you get that answer. Uh, if they do exist, I don't know. You get to. It's the same thing. As long as the two answers are equal, you get a limit. If they don't, there's no limit. So you just do the left side of f of x minus the left side of g of x. You get the answer, and then you get the other answer. So the limit of x approaches c from the right this time of f of x minus the limit of x approaches c from the right of g of x, because it's subtraction we're talking about. So yeah, for the sake of time, I'm trying to go through this pretty quickly. But just remember that same process of either like the initial part where you just find each individual limit, and then you do the property, which can be some multiplication, division, subtraction, or addition. Um, you just do that first. If one of the limits don't exist, you resort to individual sides. Multiplication, you have two different ways it can be written. So this first one, f of x times g of x, two functions multiplied, same exact thing. You find the limit as x approaches c of f of x, and you just multiply it. I'm just gonna pretend the other side is limit of as x approaches c from g of x. So same thing. If you have a limit for both, you just multiply and you get an answer. Easy. If you don't, once again, same exact thing. Left side, you multiply the left side. The limits as x approaches c from the left of f of x. You multiply that by the limits as x approaches c from the left of g of x. So just remember that left of the first function times left of the second function, and then you do the exact same thing with the other side. As long as the products you get are the same, so let's say the left side is 1 times 4, and let's say from the right side is 4 times 1. That's what they evaluate to in the limits. Sorry, they both equate to 4, so that's what it's going to be equal to. That means the limits is the same because they have the exact same products. If they were different, same as the other properties, the limit would not exist. So now let's go down to the second version. The limit of k times f of x as x approaches c. K is just a variable. It can be a variable, a number, whatever. You take out the k, and then all you do is do k times parentheses. You find the limit as x approaches c of f of x, and as long as the limit exists, you can do this. Let's just say this evaluates to L or a limit, so it just turns into L times k. That's going to be your product. Now, if the limit exists, I'm pretty sure that this just doesn't work. You can't do it in individual sides because it doesn't have another function. Division, we have a limit of x approaches c of f of x divided by g of x. So once again, you find the individual limit, and then you do the operation or the property it's asking for. You find the limit of f of x, and then you just divide that by the limit of g of x. So yeah, pretty easy. I don't know, just say this evaluates to 10, this evaluates to 5, answers 2. As long as those initial limits exist, you can just do that. If they don't, I think you get the pattern now. You do the left side of f of x, so let's just say that's left, x equals c from the left of g of x. So you just divide those. Then you get your answer. Let's just say that's 5, and then you do the exact same thing but with positives. With the positive sides, which just means the bigger side. So c from the right of f of x divided by the c from the right of g of x. I'm pretty sure this is how this works for whole properties. Let's just say you once again get 5. The limit exists. They're both 5. If they don't exist. Moving on to exponents. Exponents don't really have that, since exponents are a little bit different. So here on the left side, the first equation we have is limits as x approaches c of f of x to the r over s power. That can just be rewritten, or well, you have to rewrite it to the limits of x, the limits as x approaches c of f of x to the rs power. You write it in parentheses and you just evaluate the limit. Uh, as long as it exists, you can just rewrite it. In this example, I wrote down an 8, pretended it evaluated to 8. So you just replace the limit with the answer, and then the number or the answer you get gets the power. This power can be anything. It doesn't have to be a fraction either. That's just the variable I decided to use. It could just be singular or a fraction or whatever. It could be square root or negative 2. Negative would just mean it does 8 or s. Oh man. This becomes pretty important when doing derivatives, so remember powers. Um, all right, and now we get to what's called simplifying. So let's go. Let's see the left side first. So we're trying to find the limit as x approaches 2 of f of x. Let's just pretend I didn't solve this and do this before, but we're looking for the limits of f of x, and we have the function defined here. It's x squared plus x minus 6 divided by x minus 2. So we can't solve this if we directly substitute in. If we directly substitute it in, let's just do that in our heads. So I'm just going to rewrite the equation, but with 2 substituted in. I'm just going to do the math in my head. So that's 2 squared, 4, plus x, which is 2. So that's going to be 6 minus 6, which is, of course, just going to be equal to 0 over 0 because 2 minus 2. So the 0 over 0 is always indeterminate form. That usually means you're missing a step. You have to reduce or do something to the limit. Limits can be equal to 0, but just remember 0 over 0 is a red flag. Maybe you have to do something. So let me delete that. So basically what we do is we just reduce. We just simplify it normally. So x squared plus x minus 6 simplifies down to x plus 3 times x minus 2. Because 3 minus 2 is 1, and that's the 1x, and then 3 times negative 2 is negative 6. And then, since we have an x minus 2 on the numerator and denominator, they both just cancel out. Remember, they don't really cancel out, it just equals 1. But here's the irrelevant, so we just write down x plus 3. So that's what our new function is equal to. And then we just directly substitute again with our new function, our simplified function. And that's what I did at the bottom here. F of 2 is equal to 2 plus 3 equals 5. That is the answer of our limit. So the second form is rationalizing. So for rationalizing, give me a second. Rationalizing, here we have limits as x approaches negative 1, x plus 1 over x plus 5 minus 2. So since it's division, you find the limit of x approaches negative 1 of x plus 1 first. So I don't really have space, but I'm going to try to squeeze this in. X plus 1, and then you do the same thing, but x plus 5 square root of x plus 5, and then minus 2. And it ends up being it's in the indeterminate form. So let me just bring it back. So since we have a square root on the bottom, we have to bring it to the top, and that's what I did. So at the bottom on the bottom left corner, that's where I started. I multiplied by the inverse, top and bottom. The bottom part, I got the answer. It was x plus 5 minus 4. I simplified down to x plus 1, and then since there's x plus 1 on numerator and denominator, it simplified just down to 1, and then it ends up being just equal to x plus 5, the square root of x plus 5 plus 2, which I rewrote, and then I plugged in square root, negative 1 plus 5 is square root of 4, which is just 2 plus 2 equals 4. That's what the limit is, and that's going to work for all square roots. So that's there's another way to simplify, but that involves trig identities, which I'm not the best at, but that's about it. Thank you. See ya.